I think what I'm going to do is, what I'd like to do is to do some more Feynman rules. I'm going to write out a bunch of ones that we had on the homework, sort of after you've struggled with it yourself and got it right or not. Let's go through the rules. And the particular thing I want to focus on is the Dirac algebra stuff. So where the Dirac matrices go and how you play with them. Okay, so this is Feynman rules again. The rules always have this line, wherever you see that, is given as minus I e gamma mu. Okay, and we're supposed to stick external stuff on it in a particular way, depending what process we're after. Okay, so the homework problem had to do with e plus e minus, so it's called P1, P2, goes to mu plus mu minus. I'll make it symmetric, so P3, P4. Okay. Now, so you see there's going to be gamma mu's there, and the initial state, let's stick it over here, there's a minus I e gamma mu, and you stick around that u's and a v bar. So it's the answer is it's u of p1, the electron one, v bar of p2. Okay, so first let's just point out, because I know some people had a little trouble with this part. Remember, gamma mu is a matrix, so it's like it's a matrix. U and v are both equal to column vectors, and so then v bar looks like a row vector, and so if you multiply those together, that's a number now. Okay, so I've started with a matrix and I've stuck a column vector, a row vector, and you do matrix multiplication, and that's then a number. Okay, so that's the order they go in, and so it's always the column guy sits on this side, the row and the matrix sits in the center. Okay, then we had a propagator minus I g mu nu over q squared, and q here is p1 plus p2. I think everybody got that. And then the other side over here has it's u bar minus I e gamma nu v. So v is the antiparticle, so that's the p4, and the u bar is the particle. Okay. Does anybody want to ask anything about those guys? So that's the rules. I think the one thing that I saw several people with is putting the u's and the v's in the wrong places here. So this is always multiplied out with matrix multiplication. Okay, so now let's get fancier. Let's do the diagram that a lot of people chose, which is a good diagram to do. It's an important diagram. So we're going to do one loop diagram. So we've now got E minus, E plus, P1, P2, P3, P4. Okay. And so here's Q coming along. This guy is also Q because it turns into something, comes back. It's the same momentum. That's P1 plus P2 again. But now I've got a loop momentum here. I've got a loop, so I have to label things. So this could be, I could call that momentum K. There's an undetermined label, so I can choose it to be anything I want. Make that K, but to make this, if I draw the arrow that way, this is then k minus q flowing that way, because as you flow into that vertex, k flowing in, q flowing, k minus q plus q equals k. So that's momentum conservation. Okay. So this guy has a bunch of stuff on the outside that's the same. So if I look at the initial part, that's the same. The final part's the same. So let's write those out here. So I'll drop the indices because it's exactly the same. It's v bar minus I e gamma mu u, and way over on this other side is u bar minus I e gamma nu v. So those guys are the same as before. Okay, I might as well squeeze it in while I can. I'm going to squeeze in right here an integral d4k over 2 pi to the fourth. That's an unconstrained momentum, so it gets integrated over. And now I've got a bunch of stuff there. Well, all right, I guess I'm going to have trouble writing it, so let's do it. I'm going to, this propagator right there we have a propagator. That doesn't go from mu to nu, because here's the mu index, here's the nu index. It goes to some other label, which I'll call lambda. Let me make this one lambda and that one sigma. Let's just talk about it. Okay, so I'll make it minus, over here, minus I g mu lambda over q squared plus I epsilon, and minus over here, minus I g nu sigma q squared plus I epsilon. Okay, so this vertex there is going to carry the label lambda, and this vertex there is going to carry the label sigma. Okay, now unfortunately I need to stick a whole bunch of stuff in there. So let me just write this in what's conventional notation. I'm going to call it pi nu lambda, which is a function of q. Just lets me write it over. So this is just a name. It's actually, the name is the vacuum polarization. Okay? So there's our guy. And I'll write out what that is. Okay, so this thing that I called pi nu lambda. Well, let's imagine I'm starting right here. That first vertex there. The rules tell me I should write minus I e gamma lambda. Okay, so that's that. But now there's no external states on it, and this is a matrix. So if I think of it as a matrix, what sits on the side of it? Well, on one side of it is a propagator. In fact, there's a propagator on both sides of it. So let me just start by going off to that one side there. Sitting next to it is another matrix, which is I over k slash minus m. Okay, so sitting, here's gamma lambda, here's a propagator, and that's also a matrix. And what sits next to that matrix now, as I hit this point here, is the next vertex. The next vertex I write down minus I e gamma sigma. That's the sigma matrix. So that's a matrix. So on one side of it is this propagator, on the other side is that propagator. So let's write the next propagator there. I over k slash minus q slash minus m. And So that's the matrix. What sits next to that? Well, it's the gamma there, right? So what we've done is we've gone around and our matrix indices, if you want, this is matrix index could be, A, B, B, C, C, D, D, A, right? That turns into then the trace. Because the matrix indices run all the way around. Okay. And I could have, easy could have been a question, why did I start with gamma lambda? But you can see once I get the final answer, it doesn't matter where I started. The trace is cyclically the permutation symmetric. So if I push this propagator over there, that's the same thing. So the permutations of the trace, I could have started anywhere on that. But the main thing was what sits next to what. Okay. Yes. So that denotes the vertex that sits right there. The minus I e gamma lambda denotes that vertex. Okay. And this is. Oh, I'm sorry. I have it should be a sigma. Sigma is there. Sorry. Thank you for catching that. Yeah. So it should run gamma nu sigma, sigma lambda, lambda mu, mu. Thank you. Great. Yeah. And to be actually truth in advertising, the vacuum polarization actually has the D4K sitting in there also. So it's a function. Once I've integrated over D4K, this is the only thing left over. It's a function of this Q. So really, the D4K goes into the standard definition of the vacuum polarization. We'll calculate this someday. This isn't on our agenda today, but we will do that. It's a famous calculation. It's an important one. Okay, I think maybe that's all I'll do on the that Feynman rules, unless someone wants to ask another one. People didn't seem to have too many questions. I can write out any Feynman rule you want. Okay. The other thing I have to do is sort of a catch-up is from last time. We ran over and I didn't have a chance to do an important piece, which is building your intuition on some of the scattering amplitudes. So what we did last time was we calculated that scattering process there. Two different types, one's like an electron, one's like a proton or something. And here's the answer that we came out with. D sigma d omega was Q1 squared, Q2 squared, 64 pi squared, 1 over S, I'll remind you what that is, P1 plus P1 prime, dotted into P2 plus, actually, I think my notation it was P3, P2 plus P4. So this was 1, 2, 3, 4. I think that was my notation last time. It's that quantity squared divided by P1 minus P3 squared plus epsilon squared. Okay. So that was our cross-section. What I'd like to do is I'd like to show you quantum mechanics results come out of that. So this is a fancy field theory calculation, but it actually has the usual quantum mechanics piece in it. And to get there, what we have to do is we have to do the following. We take the non-relativistic limit, of course, But we also have to take what's called the static limit. Okay? And static means that M2, one of the particles, is much, much heavier than M1, so that it doesn't recoil. So it just sits there. That's static. So the one guy comes in, scatters off. The other guy just sits there. It's big and heavy. It's an electron scattering off of a proton. Okay. So if you remember, S was P1 plus P2 quantity squared. But if you go to the non-relativistic limit, that's dominated by the mass. That's M1 plus M2 squared, which is then, in our limit, just M2 squared. Okay. P1 plus P3 dotted into P2 plus P4. Again, in the non-relativistic limit, this guy is light compared to that guy, and the masses dominate. So this just turns into 4m1 m2. Okay, and the last thing we have to do is that P1 minus P3 squared. Okay. Well, that's, in general, it's E minus E1 minus E3 squared minus P1 minus P3 vector squared. The first guy in this limit is equal to 0. Okay? You can either do it by saying it's dominated by the mass, and so each of these energies is just mc squared, and so they cancel, and then corrections are of order p squared. When you square that, it's of order p to the fourth. Or you can do it a little bit more physically just by thinking if there's no recoil, the electron energy coming in is the electron energy going out, so it's the same. So this guy disappears in our static limit. And so this guy is then just what we would call minus q vector squared, which is minus 2 p squared 1 minus cosine theta. That's your scattering angle in the lab. Okay, so then if we look at all these guys here, S goes like m squared. There's an m2 squared that comes out of here. There's an m1 squared out of here, and there's q squared out of there. The m2 squareds are going to cancel if you think about it. Here there's a m2 quantity squared from here divided by s, which is m2 squared. So the heavy guy disappears from the whole calculation, and the cross section turns into d sigma d omega is q1 squared over 4 pi, q2 squared over 4 pi, 4 m1 squared over q vector to the fourth. Okay, so the heavy guy drops out. Okay, and now let's just go back and do this thing in quantum mechanics. Okay, so in quantum mechanics we have d sigma d omega is minus m over 2 pi integral d3x e to the I q dot x, the Fourier transform of v of r squared. So that's our quantum mechanics formula for this guy. V of R is Q1, Q2 over 4 pi, 1 over R. That's the quantum mechanical one, is basically alpha over R. In these units, you remember, when you do quantum mechanics, you actually tend not to have that 4 pi there because you're using different units. And the Fourier transform of d4, the d3x e to the I q dot x of v of r is then, it turns into, it's q1, q2 over 4 pi times 4 pi over q squared, q vector squared. So I can work that out if we need it, but let's not, unless you want to ask. And so then the answer comes out, d sigma d omega is q1 squared over 4 pi, q2 squared over 4 pi. What do you guess? 4m1 squared over q squared, q to the fourth. Okay, so you get exactly the same result. Okay, so the field theory result, so the QFT result, it has it has what you might call the Coulomb piece, and that's all that contributes in the non-relativistic limit. But it also has more. It also has things that you get in quantum mechanics by doing the exchange of real photons. Okay. Interestingly enough, that drops out in the static limit, because these transitions here on the heavy side go like 1 over the mass. But the quantum field theory result has, so it's quantum mechanics plus more. Okay. So the good feature is it reduces down to quantum mechanics, but it also tells you more. That it's not just the non-relativistic or the relativistic part. It's even more physics that you'd have to work hard to get these pieces in there, but we've got them automatically. Okay, questions? So now there we're finished up old stuff. That's the last of that. Now, what I want to transition into now, we're doing a whole section on calculations. You know, what are interesting things to do to calculate. So the next section is I'm going to talk about symmetries, ground states. I'll do symmetry breaking better. I'll do masses better. And there's a bunch of things here that go into calculations. But the very first thing I want to do is I want to show you how to calculate conserved currents and charges. So the first thing we're doing is we've seen these, and typically what I've done is I just pull them out of my head. I happen to know what the conserved currents are, so I write them down, I show you the conserved, and we use that in electromagnetic currents. But if you're confronted with a new theory, you have to be able to pull those out also. And so the calculation I want to do now is to show you how to pull them out. So you've probably heard of Noether's theorem. This theorem says that for every continuous symmetry, continuous symmetry of the Lagrangian. There's a conserved charge and a conserved current. Okay, conserved charge means that d by dt of q is equal to 0. Conserved current means d mu j mu is equal to 0. So that's when you say conserved charge and conserved current, that's what you mean. And for the last time, I won't keep doing this. These, I'll do the connection. Let's just do it one more time. Okay, the charge is the integral d3x of the time component of the current, so that if you have one, you have the other, and you have the conservation rules are also the same. If I take dq dt, that's then the integral d3x d by dt of j0, sorry, which by the equation there is d3x minus del dot j vector by the current conservation equation, which you integrate by parts. You know, this is a total derivative. And that's equal to 0 if your surface is at infinity. Okay, it's equal to, in general, it's equal to the integral dA dot j. It's the current flowing through the surface. You take that surface at infinity, and it's equal to 0. Okay, but that's not the big action. The big action, that's lore which I think you've heard of before. The real point of this is to show you how to calculate it. Okay. So there's two separate cases. One case is what are called internal symmetries, which I'll do first. And the other case is space-time symmetries, which I'll do briefly second, which is the energy momentum tensor. In practice, the space-time symmetries are always the same. They always have the same outcome. So once you see one, you don't ever have to do it again. The one you have to do again and again is internal symmetries, because there that changes from theory to theory. So someone presents you with a new theory, you have to be able to calculate this one. So that's why I'm going to do this one in detail, and the other one I'll just slip by. Okay, so what's an internal symmetry? Okay, so in this case, you leave the space-time variables you don't touch them. So for example, but you do transform the fields. So if you have a set of fields, let's just call them phi I. There's I is equal to 1, 2, 3, etc. or something. There's some transformation among these fields that leaves the Lagrangian invariant. So the transformation is phi I goes to some phi prime I, which is some Fij, some function of the fields. Leave a space there, phi j, and that function of the fields is given by some parameters. Okay, so let's imagine I had 3 fields, 1, 2, and 3, and I do an orthogonal rotation on them. Okay, the parameters then are the angles of the rotation. It's like Euler angles. And that's a perfectly good transformation. If the Lagrangian is constructed right, it could be invariant under that. Okay. So the invariance then is if the Lagrangian that's a function of phi prime and d mu phi prime is the same as the Lagrangian that's a function of phi of the original field. Okay, that's what the invariance is. Okay. So, what's the general plan? Okay. The plan is going to be that we're going to let these parameters, let me call them alpha k's, there's a bunch of them in general, they're going to turn into infinitesimal, so delta alpha k, and they're going to be functions of x. Okay, so they become infinitesimal and functions of x. Of space and time. Okay. Now, we know from the principle of least action that delta f equals 0 for any form like this. Okay? Because it's infinitesimal. So here you're using the equations of motion. Okay? So our task is to calculate delta f, and you'll turn it into the form d4x d mu j mu k delta ak of x. We turn it into that form, and then from that you can read off the conservation law. That has to be 0. Okay, so that's the game. Okay. Okay, so let's do it. So we're going to let alpha k, these parameters, be delta, turn into delta alpha k of x. Then the transform phi prime is going to be just the same transform with delta alpha sitting in there. Okay. But the place where something new happens is if I have derivatives on phi prime. Okay, that's the derivatives of Fij of delta A of x phi j of x. Okay, so there's two pieces there. There's the f of delta alpha d mu phi j. That's the usual piece that you'd expect if I hadn't made this be infinitesimal. And then there's a piece that's the derivative of delta alpha k, and I'll just write it as f prime. Actually, we're not going to actually use that, the details of that at the moment. Okay, so there's actually it's a derivative with respect to k. Okay. Okay. But it's this guy that's new, and it's that guy that's going to carry all the information that I want. Okay. So here's delta f. Delta f is the integral d for x, the Lagrangian of phi prime, d mu phi prime, minus the Lagrangian, and let me put a prime on the Lagrangian too, phi d mu phi. Okay, so there's what we have to do. Well, just by doing the variation, here's what you do. It's the integral d for x. It's the variation of the Lagrangian with respect to d mu delta alpha k times d mu delta alpha k plus the variation of the Lagrangian with respect to alpha k delta alpha k. Okay, and as always you do the following. You integrate by parts. This turns then into d for x. Delta alpha k can be factored out there. It becomes minus the derivative Lagrangian with respect to d mu delta alpha k. And then the second term is unchanged. Okay. So, any change, there's nothing special about it. Now, we've just derived the following. D mu delta L prime delta d mu delta alpha k equals the derivative of Lagrangian with respect to delta alpha k. Okay, so playing silly math games there, we've gotten this. That's general. But now comes the main feature. Is this last term is 0 if there's an invariance. If the invariance, then we have then the variation with respect to delta alpha is equal to 0 just because our invariant statement up there, let's move up to it, was that if I made this transformation, the Lagrangian was independent of that. And the only thing it can depend, this was a constant, but if I'm just asking what's the variation with respect to alpha, that's 0. Then I could take it to be a constant. Okay. So the statement is that this L prime is, if the invariance exists, doesn't have any dependence on alpha k. And this then is the way to calculate the current. So jk mu is the current, is the variation of the Lagrangian, this transform Lagrangian, with respect to d mu delta alpha k. That's equal to the Noether's current. Okay, and the Noether's equation then, or the equation of motion that I derived there, is d mu jk mu equals 0 if there's an invariance. Okay. Let's do an example. Maybe that may help. Okay, the example is, let's take a phase invariance. So phi, it being a complex field, goes to phi prime, which is e to the minus I alpha phi. Okay, so the Lagrangian is d mu phi star d mu phi minus m squared phi star phi. And that's invariant. So the Lagrangian is a function of phi prime, is the Lagrangian is a function of phi, because that phase drops out. Okay. Okay, but now I let alpha turn into delta alpha of x. Okay. Then phi prime is 1 minus I delta alpha of x, phi of x. Okay, but now because of the derivative terms, that's not going to be an invariant. So let's look at what comes out. So it's is L prime, which is a function of phi prime, d mu phi prime, is derivative of 1 plus I delta alpha of x phi star of x d mu of 1 minus I delta alpha of x phi of x minus m squared phi star phi. Okay, so the phase dropped out over here. Okay, so there's no contribution from there, so that's an invariant still. And now, if you look at these pieces here, there's two pieces. There's the piece where the derivative acts on the phi's, and then the phase drops out overall, so there's no phase in the final answer as usual. Or there's the derivative can act on the delta alpha. So this turns back into the Lagrangian of phi d mu phi. And then there's a piece which is plus I derivative mu delta alpha. Okay, and we're going to collect up those pieces. So the first one is here, I derivative here is phi star. This derivative acts on phi, so it's phi star d mu phi. And then the other one is, this guy comes with a minus I, becomes minus, or so the I's already out in front, minus d mu phi star phi. Okay, and then since it's infinitesimal, you drop the next term where there's delta alpha squared. Okay. So then our construction says that the Noether's current, J mu, is the derivative of the Lagrangian, the shifted Lagrangian, with respect to d mu delta alpha. And there's the d mu delta alpha piece. So I just take the coefficient of that is I phi star d mu left minus right phi. And that was always our current before. Okay, so there's how we knew this current should be there. The phase invariance leaves this conserved current. Okay, so it's the Okay, you can give it various names. You could call it the number current. You can call it the probability current. But there's something, if you add an electric charge, it's an electromagnetic current. Okay. If we do okay, so any questions about that? Let's do the same thing for the Dirac field. You can sort of see it easily now. We take the Lagrangian is psi bar I d slash minus m psi. That transforms into psi bar e to the I alpha I d slash minus m e to the minus I alpha psi. And at this stage you can sort of do it in your head. If alpha is a constant, this is an invariance because it just passes through the derivative. If you make alpha a function of space-time and then make it infinitesimal, there's a derivative acting on alpha. The derivative, it's gamma mu, derivative of alpha. The i's cancel, and you can sort of do it in your head. You let alpha goes to delta alpha of x. Sorry, come on, erase. There we go. And then J mu is the variation of the Lagrangian, the shifted Lagrangian with respect to d mu delta alpha of x. Turns into just psi bar gamma mu psi, which was always our current there. The gamma mu comes from this gamma mu sitting right there. The derivative acting on that gives you. So that's our current again. Any questions? All right, let's do energy and momentum then, if there's no questions. I'm going to do this quickly. The symmetry is the following. The symmetry is we're going to let phi of x goes to phi of x plus a. Okay? A is going to be, so this is the transition, then x mu goes to x mu plus a mu. That's a space and time shift. Okay. Then we know that if there's no explicit dependence, then S prime is the integral d for x of L of phi of x plus a, d mu phi of x plus a. And you just shift the integration variable to x plus a. If there's no explicit x dependence, then that's equal to f. You shift the variable and everything's invariant. Okay. Now, this might not be the case if you were doing some quantization in a cavity and you had some boundary conditions and all that stuff, but that's things where momentum isn't conserved. If you have a cavity and boundaries, then momentum isn't conserved. Okay, so there's the invariance. And the pathway, I won't, as I said, I won't do it all as much, is the same. You write a mu is delta a mu as a function of x. Delta s is equal to 0 for any delta A mu. And then you go into the heart of it, and play silly math games, and write this as the d mu, or I've got it, mu, so it's d nu t, that's t nu mu delta A mu. Okay. Now, so there's one label that's summed over this. So there's a separate current for each mu here. So there's an overall mu there, and I've got my labels backwards from convention, but that's life. But we've now got a conserved quantity that's 0. Okay. And let's just write out what that is. So if you play these games, I have all the work, but looking at the clock, I don't think I'm going to do it. One defines T mu nu is the derivative of the Lagrangian with respect to d mu phi, d nu phi, minus g mu nu times the Lagrangian. This is the energy momentum tensor. Okay. That's the guy who's conserved, so keeping the indices in more conventional notation now. dt mu nu is equal to 0. So there's four conserved currents here. For the 4 symmetries. Nu is equal to 0, 1, 2, 3. That's a nu. Okay. Okay. Well, T00 is the derivative of the Lagrangian with respect to d0 phi times d0 phi minus the Lagrangian. So it's just G00 is 1. If you remember our early construction, that's our canonical momentum. This is our Hamiltonian density. This is the energy density. Okay. T0I is the derivative of the Lagrangian with respect to d0 phi, then di phi is multiplied by. It's easy to do that. That just turns into d0 phi di phi. Okay. So that's a spatial vector, and if you look at what this is, this was the momentum density. Which I did back in Basics 3. If you want to go back and see that that's the momentum, what we did back in this unit here, Basics 3 unit, was we wrote out what this looked like using field quantization and showed that the integral of this was the momentum carried by the particle times A dagger A. Okay? And so we end up with 4 conservation laws: the conservation of energy and momentum. The conserved charges are then integral d3x of t00, and p, which is the integral d3x of t0I. Those are conserved. And you get conservation laws. Okay. So that's a quick derivation of it. It actually is a little bit more painful than the derivation we did to do the writing of the variation of the action in that particular form. But given what we've done, it should be obvious. It should be doable. Okay. Yes. So the energy now is a charge. In this language, it's a charge, and so is the momentum. It's a conserved charge, a conserved quantum number. Sometimes people say conserved quantum number, but that's the phrase charge has this general definition now, because we've now generalized the idea of a current to include the flow of energy. If we do this I actually don't have it carried along here. If we do it for Maxwell's equations, you get this being half e squared plus b squared, and this being the Poynting vector, the flow of energy, comes out naturally. So they live in the same beast. In a relativistic theory, they're components of the same beast, the energy momentum tensor. Okay. Any other questions about it? Now, so the theories I just wrote down there were free field theories. Okay, but part of the game of this is to read out general invariances. So very often the free field theory has a symmetry, the interactions break it, and you should be able to look at these things and just see them occurring. So let me do an example. Let's take a proton and a delta plus. The delta plus is a heavier particle, has the same charge as the proton. It has a different spin, but let's just pretend it's the same. Okay, so the free fields would be psi star proton, it's I d slash minus m, psi proton, and let's do psi star delta. I'm actually being a bit sloppy here because I don't really want to tell you how to write out the field for a spin 3/2. Delta carries spin 3/2, which I'm not that interested in right now. I don't want to tell you how to write that out. It has no deep meaning for what we're about to do. Okay, but you can see from this, just from the work that we did before, this Lagrangian has two invariances. Psi p is e to the minus I alpha p, psi p, psi delta goes to e to the minus I alpha delta, psi delta, and you'd end up with two currents. You'd have a proton current, psi bar gamma mu psi, with protons, and you'd have a delta current, Okay, so there's two invariances. But now let's imagine that, as happens in the real world, there's a transitions. Let's write out a Lagrangian that has some transition that takes a delta into a proton by emitting, well, in the real world it's a pi zero. So you take a delta proton emits pi zero particle. There's a transition. Okay. Now this is not invariant now. Okay. And you're not, at least under separate invariances, if I try psi proton goes to that one, this isn't invariant. And what you'd find is if you found, then you would look at d mu j proton mu would turn into g psi proton psi bar delta pi 0, not equal to 0. Okay, so if you'd just done the equations of motion or did the original derivation that we did there, you get this. That's not equal to 0. And that's a good thing, because now proton number isn't conserved. Here's a process that had no proton number, and proton number suddenly appears. And likewise, delta number is also not conserved. But there's still conserved an overall number. So if you wrote psi proton goes to e to the I alpha minus I alpha psi proton, psi delta goes to e to the minus I alpha psi delta. Okay, that's with the same alpha. Okay. Then the conserved current, J baryon, let's call it, is J proton plus J delta is conserved. So separately, our conservations have been broken, but there is still a conserved quantum number. Okay, so looking at the Lagrangian, looking at these pieces, you can tell what's conserved, what's not. And you can even break the baryon number Okay, so this is baryon numbers, typically called. To break baryon number, you can write a perfectly good interaction. The Lagrangian could be, let's make it some G prime, some other interaction. Psi bar the positron, psi proton, pi 0. Okay. Now you look at that, and what does that do? Well, that takes a proton into a positron and pi 0. Well, that seems not to occur in nature, so it's not seen so far. Though it is predicted in grand unified theories. Okay, so if that were to exist, then baryon number is no longer conserved either. Though there's still a conservation law. There's still if you had psi proton goes to e to the I minus I alpha psi proton, psi delta, e to minus I alpha psi delta, and psi positron goes to e to the minus I alpha psi positron. That conserves baryon number minus lepton number. Yeah, there isn't anyone. Well, I'm imagining adding it to the interaction that was up above. So I needed that from up above. Okay, so I'm sort of doing this sequentially. Okay. So that's all right. So I guess looking at the time, I don't want to start the next topic right now. I'm going to stop right there. But this has all been about then reading Lagrangians, picking out the symmetries, what are the currents, how do you get them. The next time we're going to do ground state energies, symmetry breaking, and some very interesting work on why names don't count. I'll write out a Lagrangian using two different names and show you, even though they don't look at all the same, that the results are the same. Okay, so it's something I always have fun doing. So let's stop there. Next time I come back to symmetry breaking, ground state energy, masses, and this Hogg's theorem that names don't count. Good. Let's see. I'll give you yours there. Oh, you want to take folios? I think I gave you yours.